What you're about to hear isn't magic, and it isn't a one-size-fits-all solution. This video is built on historical research, documented science, and educational exploration. It is not professional construction advice, not a building code guide, and not a replacement for a licensed contractor or insulation specialist in your area. Every home is different. Every climate is different. Every local code is different. Our goal at Fix Viral Secrets is simple: to dig into forgotten knowledge, practical science, and overlooked methods that most mainstream channels never bother to cover. We don't make promises. We share what's been documented, what researchers have explored, and what some homeowners and builders have found useful. Then we let you decide. Imagine holding a piece of material in your hand that's mostly air. 95% air to be exact. It weighs almost nothing. You could rest a brick on top of it. You could hold a blowtorch to one side and barely feel warmth on the other. And the raw ingredient sitting right beneath it? Sand. The same sand you've walked on barefoot at the beach. The same sand your kids build castles with. The same sand that costs almost nothing and exists in nearly unlimited supply across this country. Now imagine that a material made from that sand has existed since 1931. That researchers confirmed it could outperform fiberglass insulation by a significant margin, that it was written about, studied, and then, slowly, quietly, became one of those things that most people today have simply never heard of. That material is aerogel. And today we're going to talk about what it is, where it came from, how it's made, and what it might mean for the average American homeowner who's tired of paying sky-high energy bills and working with materials that itch, break down, and underperform. It starts with a man named Samuel Kistler. The year is 1931. America is deep in the Great Depression. Resources are thin, innovation is fierce, and a chemist at the College of the Pacific in California is working on something that sounds almost absurd on paper. He's trying to take a gel, a substance that's mostly liquid, and remove all the liquid without letting the solid structure collapse. Think about what happens when you let a grape dry into a raisin. The skin shrivels, the structure collapses inward. That's what happens to almost every gel when the liquid evaporates. It shrinks, it crumbles, it loses its shape. Kistler wanted to prevent that. He wanted to keep the architecture of the gel intact, all those microscopic chambers and walls, while removing every last drop of liquid inside. And he found a way to do it. Using a process called supercritical drying, Kistler essentially brought the liquid inside the gel past a specific pressure and temperature threshold, where it transitions between liquid and gas without surface tension, which is what normally causes the collapse. The result was a material that was structurally solid, but internally almost entirely empty space. He called it aerogel, and it was, by every technical measure, remarkable. But here's where it gets interesting. Kistler's first aerogel was made from silica. And where does silica come from? Silicon dioxide, the main component of ordinary sand, the stuff you can find on nearly any coastline, riverbank, or desert in the continental United States. That's not a coincidence or a poetic detail. That is the literal foundation of aerogel chemistry. Sand processed into a sol gel, treated with the right chemistry, including acetic acid, which is the main compound in plain white vinegar, can be transformed into one of the most thermally efficient solid materials known to science. Now, let's be honest about something right here, because this channel doesn't do hype without substance. The aerogel Kistler made in 1931 was not something you could whip up in an afternoon with materials from the dollar store. The supercritical drying process he originally used required industrial equipment, high-pressure autoclaves running at temperatures and pressures that are not safe for home workshop. But science doesn't stay still. And over the following decades, researchers began developing a more accessible version of the process, one that replaces the high-pressure supercritical step with a chemical exchange method called ambient pressure drying. This approach uses solvents and surface modification chemicals to prevent collapse during drying at normal atmospheric pressure. It's still chemistry, it still requires careful handling, but it brought aerogel production significantly closer to the reach of a well-equipped, safety-conscious experimenter. And this is where most people stop looking. Because when ambient pressure aerogel synthesis began appearing in peer-reviewed chemistry literature, papers out of universities, material science journals, open access research databases, the mainstream conversation had already moved on. Industrial aerogel was being manufactured at scale for aerospace, military, and high-end construction. The DIY potential was acknowledged in academic circles, but almost never translated into accessible language for the average person. So let's translate it now. Silica aerogel starts with something called a silica alcohol. To make that, you need a silica source. This can be tetraethyl orthosilicate, known as TiOs, which is a laboratory-grade silica precursor, or it can potentially be derived from agricultural silica sources like rice, husk ash, or processed from fine silica-rich materials including highly purified natural silica sand. The gel formation process typically involves mixing your silica source with ethanol and water, along with a catalyst to initiate the sol-gel transition. This is where acetic acid, household white vinegar, enters the picture. Acetic acid acts as an acid catalyst in the sol-gel process, helping initiate the cross-linking reaction that turns liquid silica solution into a three-dimensional gel network. The chemistry here is real. It's documented. It's been reproduced in university labs across the country. Vinegar, or more precisely the acetic acid in vinegar, is used as a pH adjustment catalyst in accessible silica sol-gel synthesis. It's not a folk remedy. It's actual chemistry that works under the right conditions. Once your silica gel forms, it sits, typically for hours to days, allowing the structure to strengthen through a process called aging. Then the liquid inside the gel pores must be exchanged, typically swapped out for a lower surface tension solvent like ethanol, and then the surface of the pores is chemically modified to make them hydrophobic, meaning they repel moisture and resist collapse during drying. The final drying step, done at ambient pressure over time, leaves you with a lightweight, porous silica structure that is, in the right formulation, genuinely aerogel. But here's what matters: the thermal performance. Standard fiberglass batt insulation, the pink stuff rolled into walls across millions of American homes, has a thermal conductivity of roughly 0.04 watts per meter Kelvin. That's the standard. That's the baseline most homes are built to. High-quality silica aerogel has a thermal conductivity as low as 0.015 watts per meter Kelvin under normal conditions, and lower still in specialized configurations. That's not a small difference. That's a fundamental improvement in how efficiently a material resists heat flow. In practical terms, a much thinner layer of aerogel can provide the same insulation value as a significantly thicker layer of fiberglass. Researchers at institutions, including Lawrence Berkeley National Laboratory, have studied aerogel's insulating potential in building applications. Commercial aerogel blankets and panels are already being used in high-performance building retrofits, particularly for thin wall insulation in historic buildings where space is limited. Before we get into the step-by-step process, I want to hear from you. Drop your state in the comments right now. Are you in a cold weather state like Minnesota or Montana, where insulation is everything? Or somewhere like Texas or Arizona, where keeping heat out is the battle? Have you ever tried DIY insulation projects before? Fiberglass, spray foam, mineral wool? Tell me what worked and what didn't. And if this kind of deep dive practical history is what you come to this channel for, hit subscribe. We don't post fluff. Every video on Fix Survival Secrets is built on documented research and real-world practicality. More people need to hear this kind of content, and your subscribe helps make sure they find it. Now let's get practical. What follows is a research-based overview of the ambient pressure silica aerogel synthesis process as documented in open access scientific literature. This requires proper safety equipment, careful chemical handling, and is not recommended for anyone without a basic understanding of laboratory safety. Always work in a well-ventilated area. Wear chemical-resistant gloves, eye protection, and appropriate respiratory protection when handling chemical solvents. Consult safety data sheets for every chemical you use. Keep open flames away from any alcohol-based solvents. The first step is gel formation. The most accessible approach uses TEOs mixed with ethanol and water in specific molar ratios, with a small amount of acetic acid added to initiate the acid-catalyzed sol-gel reaction. The mixture is stirred and allowed to gel, which typically takes anywhere from a few hours to a day, depending on ratios and temperature. Some researchers have explored rice husk ash as an alternative silica source, which requires alkaline extraction and acid precipitation, but produces viable silica for sol-gel work. The second step is aging. The gel sits in a sealed container, sometimes submerged in ethanol for a period of 1 to several days. This strengthens the silica network and prepares it for solvent exchange. The third step is solvent exchange. The water and reaction byproducts inside the gel pores are gradually replaced with pure ethanol through a series of soaking steps. This step is critical. Any remaining water can cause cracking during drying. And the fourth step is surface modification. The interior surfaces of the silica pores are treated with a silylation agent dissolved in ethanol, which chemically bonds to the silica surface and makes it hydrophobic. This is the step that prevents the pore walls from being pulled together by surface tension during drying. The fifth and final step is ambient pressure drying. The modified gel is dried slowly at room temperature or with gentle heat, typically under 150 degrees Celsius, over a period of days. Done correctly, the structure retains its porous aerogel architecture. Here's the honest picture. Commercial aerogel insulation exists right now. You can buy aerogel blankets, panels, and granules from suppliers today. The reason it isn't in every American home isn't because it's been suppressed. It's because cost per square foot at commercial scale has historically been higher than fiberglass, and the construction industry tends to move slowly on new materials. That gap has been narrowing. As ambient pressure synthesis has matured and more manufacturers have entered the market, prices have come down. Some builders and energy-conscious homeowners are already using commercial aerogel in specific high-value applications: attic hatches, rim joists, thin walls, pipe insulation. DIY aerogel synthesis remains a project for serious chemistry hobbyists with proper equipment and safety protocols. It is not a weekend garage project. The chemicals involved require respect and proper handling. For most American homeowners, the practical takeaway from aerogel science isn't make your own. It's understand what this material can do, watch the commercial market, and consider where it fits in your next renovation. Samuel Kistler discovered something in 1931 that most people today have never heard of. He made solid material out of air and sand. He documented it, published it, and moved on. The science lived in journals and labs for decades before anyone thought seriously about what it could mean for an ordinary house on an ordinary American street. Over time, the technology became more accessible, the chemistry became better understood, and now, right now, the gap between what's possible and what most homeowners know about is still surprisingly wide. That's why Fix Vital Secrets exists. Not to sell you something, not to promise miracles, but to put documented, real, research knowledge in front of people who are ready to think differently about the materials and methods available to them. This video is educational. It is not professional advice, not a building permit, and not a guarantee of results. Always consult a licensed professional before making structural or insulation changes to your home. Local codes vary. Material performance varies. Your situation is unique. If this gave you something to think about, share it with someone who would want to know. Drop your thoughts in the comments, and if you haven't subscribed yet, now is a good time. Next time, we're going into another method that's been sitting quietly in old engineering manuals, something most modern builders have completely walked past. You won't want to miss it. This is Fix Vital Secrets. Practical, documented, forgotten. Until now.